session. And then we wrap up the session. So as you all heard, we are going to record the session, only the presentation that Severine does, and I hope that's okay. So for those of you who don't know AI Sweden very well, AI Sweden works on accelerating the use of AI for benefit of society, our competitiveness, and everyone living in Sweden. This is our very clear mission, and everything we do kind of ties back to this. So this is why we do this. So the deep dive sessions is, we created this to support the key roles and to provide an arena so we could all discuss. We know how fast everything is moving, and while you're expert in one topic, there are so many new things coming and you need a place to discuss it. So this is why we created the deep dive sessions. So we define this as for a specific kind of people, that's data scientists or similar functions. And we discuss this a lot with our partners, like who is this for and how will this be useful? So we define this as someone who is flexibly carrying out analytics, is able to run, extract knowledge data, and talk to different people, produce and also present in a way that people understand. So this is a rather broad role, but we all know that that's what data scientists do. Today we have Severine, who is a developer at AI Sweden for the language technology group. And we are thrilled to have her here. She has worked on this quite extensively for her master's, and she works on this in her daily work life. We also have Carolina. I was a bit quick there. Carolina is our really great, fantastic project manager for the deep dive sessions. And we planned a lot on what to do, how to formulate it. So today she will act as the host. She will man the chat and also do the breakout rooms and everything that is related to that. And me, I'm Vinuta. I'm senior data scientist at AI Sweden, and I'll act as the moderator for the session. So as you know, now we have the information extraction part. Then we'll go into a breakout session. You'll of course see these questions again, where we'll discuss for your area of work, where can you use it? Then we take a little break and ask you to fill a small survey of 3 or 4 questions so we understand who's attending these sessions. Then after the longer session on transformers, we go into breakout session 2 for these questions. And then what we can do is to have a community going. You're all welcome on the AI Sweden partner Slack. And then we would love to have your feedback about this session. So I will stop sharing now. And Severine, can you start, please?
I will start sharing my screen as well.
Yeah.
Share. Okay. So now you should see my screen only in presentation mode.
Yes.
And I hope everyone can hear me, yes, because you need to answer me. Okay, great. So welcome everyone. Today I will, as Vinuta already told you, explain 2 parts. So in this first part, I will start about information extraction and how attention can be used to improve information extraction. And this way you can already get a feeling of what attention is. And then we will, in the second part, go in more details about attention, and as well go more into detail what transformers are. So yeah, let's start. So the first maybe question that you will have is, what is information extraction? So if you want to read more about this topic, you can always go to this link. But information extraction is a very basic task in the natural language processing field. So what you have is that nowadays everybody creates new tweets every day, writes new articles and emails. But this are all kind of unstructured data. It's quite hard to handle this by computers. So what information extraction now tries to do is get all this unstructured data, puts it through an algorithm, and then extract this more useful parts or more structured data that can be handled by computers. So this maybe seems a little bit fluffy, but I think it will become clear with a more like a concrete example. So given this part of unstructured data, which is just a piece of text about the royal couple Harry and Meghan, we will apply 3 tasks, which are called named entity recognition, co-reference solution, and relation extraction. And the combination of these 3 tasks will give us the act of information extraction. So what is the first one? The first one is named entity recognition, and this task will try to find the named entities in a text. So here it is Harry, Meghan, Clarence House, etc. Then in the second step, we will try to cluster these entities together. So we have different, so we will try to cluster the entities together that refer to the same real world entity. So for example, Meghan and Meghan, we know that it refers 2 times to the Meghan Markle entity in the real world. And once we have these entities found in our text, we can start finding relations between these entities. So we've got Meghan and then Harry, and the texts say that they are together. So we kind of know that Meghan and Harry have a relation. But we as a human, when we read this text, actually have an advantage. Because we already know a little bit about Clarence House, this is like a royal palace. And we also, so this makes us think that Harry and Meghan actually refer to the royal couple, Harry and Meghan. But when the algorithm sees this, he doesn't know anything about Clarence House of Harry and Meghan because he doesn't have this background knowledge that we know. So what we try to do is to improve information extraction, we will try to leverage this external knowledge or this background knowledge that we as humans have when we read text. And we will try to do this using attention, and we will find this external knowledge in Wikipedia and Wikidata. But of course, you can have different sources of external knowledge. So very concrete, what in this first use case I would try to explain is we try to improve a current information extraction algorithm by leveraging or adding this external knowledge into this algorithm, and therefore we will use attention. So I will try to show why attention can be useful for this. But first, I will try to explain the method that we use for information extraction before I can use how we applied attention to it. So of course, there are a lot of different algorithms to perform information extraction, and they have changed over time. For example, in the very first beginning, when you did named entity recognition, so to find the entities, you just wrote down all rules, so specific rules. So for example, if you wanted to find a city and a country, you would just write down rules. X is located in Y, and then find these exact sequences in text, and then you find these entities. But as you feel, this is not really scalable because there's so many ways to write down about entities that it's very hard to write down all the rules. So then we went to more statistical parts where you will be like counting how often certain words come together, which are then the n-gram models. If you heard about them, but it's not so important for this topic. And then we moved into supervised machine learning, where we use like smaller models with very sparse input vectors. And then we came to deep learning. And I will first try to explain why deep learning is so good for the NLP community. Well, it is exactly because deep learning allows us to represent text way better in the mathematical world. Because originally, when we have only this statistical or not this supervised linear models, so the machine learning type, what we did is when we had to represent text, because you have to represent text with a vector, what we did was like we created one big vector, which had the full size of the vocabulary. It was filled with zeros. And if you want to represent the word king, you just add a 1 on that position. But as you feel like all the zeros don't really contain information, so it's like wasted space. So what we did then, what the deep learning allows us to do is like to create, for example, for the word king, a way smaller vector embedding with real numbers in them, which actually contain information about that word. So what the goal would be is that these embeddings, for example, if you got synonyms, that these embeddings of these synonym words lie really close together in this mathematical representation space. But how do you get these? Well, what we think of is that synonyms often occur in the same context. So synonyms are used surrounded by similar words. So this is also how we use then this training objective to train this word embedding. So what we say is we would give to a feed-forward neural network. So we input, given these this neighboring words representation, please predict the word that was in between this words before and words after. Or you can do like a very hard task that is even unsolvable for human beings. It's like, here is a word, please predict the context. But there's so many possibilities. But it's a way of learning the context given a word. And this is actually a very basic deep learning neural network. What you do is you input an embedding, which is just often a randomized matrix, where every row represents an embedding of a word. And for example, and then you pick a size of the embedding, often there's like 200, which is K. What you then do is, for example, if you want to go back to this example, we pick the random embedding for learning, never D in mind. We take the average of it and we feed it into one layer of feed-forward neural networks. This will then produce a result and say, I think that in the entire vocabulary size, the word that we are looking for is exhaust, I think, exhaust. And then if it's wrong or right, it will create a loss function and then backpropagate back entirely into this matrix. And in the end, this will be initialized with useful embeddings, and you can actually throw away this part of the model. So this is the big advantage that deep learning gave to NLP, to make this dense representations that are more useful than these sparse factors. So that's also why for my information extraction, or currently mostly deep learning techniques are used in NLP. So now I will come back to the exact algorithm that I used to do information extraction. So to come back to the example I first gave, so about the couple Harry and Meghan, what you do in the first step is create mathematical representations for it. So you will split it into tokens. And then what you do next is take these trained embeddings, which are, you can just take them, they're available online. So you represent each word by mathematical representation. What you then also try to do is actually, but that's maybe a little bit too specific, but we also put them through bidirectional LSTM, which allows us to incorporate, to make this embeddings a little bit more personal, such that in this case, the we that you see here also will contain a little bit of information of its neighboring words. So that's why I call it a contextualized embedding. So these are then the words. What we will then do is like take these words together, because we want to find named entities, and named entities can be just more than one word. So it could be Meghan Markle, and Meghan Markle is 2 words. So we create these spans, and once we have these spans, we have actually 3 feed-forward neural networks in parallel. So in the first neural network, what you get is you get the span, you feed in all possible couples of spans that we have, and this will then say there is a relation between this, and then what type of relation there is. Then we've got the co-reference score, which we will also fed all possible combinations, and then it will say they refer to the same or they don't refer to the same person or real world entity. And then the next score will only receive one span at a time. I will say this is a named entity, and then it will also give it some text, like this is, for example, Harry, and we know he's a male, he's a person, and he's a royalty. So this is how the information extraction worked. And now the interesting part. Where can we now leverage this background knowledge that we have? So what we tried to do was to enrich these representations before we feed them to these parts that actually determine the outcome. So what we will do, we will add embeddings that will represent this external knowledge to the spans. But then comes a big question, what external knowledge? Like we cannot just append the entire Wikipedia in one embedding. So I will first explain this a little bit. So this external knowledge given a Wikipedia page, Wikipedia actually consists out of text, and text actually linked to other Wikipedia pages. So here we see the text biracial, but this text biracial is linked to the other Wikipedia page multiracial. And this allows us to request from Wikipedia a specific text. So for example, if we request in the entire Wikipedia Megan, to which other Wikipedia pages is the text Megan linked, then we can see that it is linked to Meghan Trainor, Meghan McCain, Megan, etc. But it even allows us to do more. We can also define a prior. So for example, we can see how often does Megan refer to Meghan Trainor, how often does Megan refer to Meghan McCain. So we actually count the amount of times that the word Megan refers to a certain Wikipedia page. So in this case, the word Megan referred in 40% of the times to the Wikipedia page Meghan Trainor. So, and then of course, we can also train from this Wikipedia pages an embedding, and that's the embedding that we want to append to a specific span. So now we have all the components. Let's try to fit them together. So our end goal was to enrich this span Megan, so to add useful information to this text span. And therefore, we will look up the word Megan into a dictionary created by Wikipedia. And this dictionary will give us back like this list of candidates that it can refer to. And it will also give us this prior back. And we have for each of these candidates also a mathematical representation. Now the question is, how can we transform this list of candidates in just one entity embedding that we can append to Megan? Therefore, we have three options. We can just take the true solution, so the correct one, so in this case, Megan, the Duchess of Sussex. But of course, in an unlabeled data set, this is unknown, so this is not possible. Another part would be, we'll just use a prior. We will use the knowledge that we got from Wikipedia, and there we saw that Megan, in most of the cases, refers to Meghan Trainor. But this doesn't allow us to exploit like the information we got locally around Megan. So that's why we used attention, where we can look at Megan and see that Megan actually, based on the context, referred to Megan, the Duchess of Sussex. So I will quickly explain how this attention then, how can we define these attention scores? There are different ways to calculate attention. The most easy way would be that you take like this text span, and then you take a dot product with each of these entity embeddings for each possible candidates, and this just gives us a score. And the ones that are like most similar is most probably the most important one and will have the highest score. But then the embeddings need to have the same dimension, which is a little bit of makes it a bit harder. What we did was using a feed-forward neural network, which is called additive attention. So what you do is you take the text span of Megan, and for each candidate, you will feed it into a feed-forward neural network, and this will be trained to generate the score as well. So to make it very concrete is in the Oracle configuration, you just append this entity embedding. In the prior configuration, you would append a weighted average of the embeddings using the priors as the weights. And then attention, you first calculate the scores by passing them through this feed-forward neural network, which you of course need to train. And then you see in this case that attention is able to select. This is, by the way, a real example out of the thesis. So you see that it's able to select, like, based on this text span Megan, that it really refers to Megan the Duchess and not the Meghan Trainor one. And then you append this entity embedding. So more concretely, now we saw what information extraction is. We also saw how we can now add this external knowledge using attention to improve the performance of the algorithm. And now I'll give you like a very high level some results. I left out the specific numbers, but like what did it actually do is for the task of coreference resolution is where you have to cluster mentions that are the same. we see that it became more fine-grained. So adding this enrichment to the span, it was able to differentiate better. So if you had one article talking about Google and Google Street View, before they ended up in one cluster, but now it was able to say like Google, that's the company, and Google Street View, that's one of the products. And then for the named entity recognition, where you had these entities, we had to append this labels to it. And when we enrich the span, it is able to find the more rare entity types that occur less often in the data set. And then we see if they occur less than 50 times, we see a big increase in performance. So apparently it kind of worked that we were able to enrich this spans with this external knowledge using attention. I hope this was a little bit clear what information extraction was, how you can use it to do, and how attention can be used to add this external knowledge. And now we would also like you to think about this question, if you could maybe use information extraction in your current work field, or you even use this leverage of external knowledge. So I think we will now go into breakout rooms. Do I stop sharing for now, or?
Yeah, I think maybe leave it so
Yes.
they know what the question is.
And then we are trying to make some breakout rooms.
So we have some time for this discussion.
And
have
did we say
nine-
10 minutes or?
We have till 9:40.
9:40.
Yes, we have till 9:40. And then we come back to the main room and each of the groups present.
Great. Then
So feel free to talk to each other about what you do, introduce yourself, and then go into the question. So we have 15 minutes to do that.
I stop recording and then I start the breakout rooms.
Recording. You can share your slides, Severine.
Yes, okay, I will start with sharing them again. Here we are. I think now everything is set again. Okay, perfect. So then we're ready for the second part of this deep dive session, which will be about transformers. So I hope it is easy to follow along. As I will try to explain you what transformers are, a little bit maybe in a high level way, but I hope you will kind of get the idea behind it, why it works. So let's start with a very high level view about transformers. What are they? They are language models. And what are language models? These are just a type of model that try to model the probability of text. How does normal text look like? And then it combines this idea of it being a language model with the architecture that heavily relies on attention. The principle I explained earlier as well. And why does it rely on attention? Because this attention will allow to have long-range dependencies in text. So if you got a word, you can refer back in time to a previous word and still find these dependencies between them. And we will also see that attention allows to be omnidirectional. Maybe this still sounds a little bit vague, but during the presentation, I will try to explain next why attention has these two properties. But let's first start with what are language models, because I'm not sure if that's very clear at first. So what's a language model? As I said, it tries to model the probability of text. So how do we train this? So we can actually give this model a piece of text, and then it will say like how likely it is that this is natural text. So if you give it a bad piece of text, it will say like, I don't think this is really natural text. Or hopefully if you give it correct, that's the text is like, yes, this is how text should look like. How do we train those models? We do this by giving it a piece of text. So for example, input, where are we? And then we ask the model to try to predict the next word. What's the logical sequence of the sentence? In this case, the ideal outcome would be going. So of course, language models in say can be used as well, for example, to do like autocomplete or to correct errors, because it can see like this is not a very logical sentence, this would be a more logical one, and correct your errors. But that's maybe a little bit limited use. If transformers were only able to do language modeling, it would be not as big of a deal, I think. But what we see is that these language models, the fact that they have this ability to model the text characteristics, that they form a really great baseline to then fine-tune this model, because this model understands text and then you can adapt it to a more specific area. And a second thing that makes this language model so good is that we can train them very well, because to train a language model, you have data in abundance. You just need text. It's the only thing you need. You don't need any labeled data. So this allows us to apply like the scaling laws. And what does this is one paper about it. And what does this paper say is like, if you have, how do I say this? So if you have these, these scaling laws, and what we see is when we make the model size increase, and if we have add more data, and so more compute, we see that generally the model becomes way better at modeling language. So actually this paper makes a quite strong statement as well. And they say that the performance of a model actually strongly depends on the scale of your data. And actually on that case, only weakly on the shape or the architecture that you put into it. So that's why language models are very good, because we've got this data available. But this also brings us to the point that today we've got these huge transformers models, as for example, GPT-3, which contains 175 billion parameters and needs huge amount of data. I think it was trained on some terabytes of data, which is a lot, and also use compute resources. Of course, afterwards, hopefully GPT-3 is not fully free available. You need your API, but you can then use it for your own property, but you need this big compute to be able to train them. For example, there's a rough estimate. They say that like one training run of such a model would cost 4.6 million euros, which is quite a lot for just one training run. So yeah, we can say these are quite expensive models. So then now what we have is this very big language model. How can we now adapt it to specific tasks? Well, so you've got this training of this language model is often called pre-training. And then you take this model and take a labeled data set, which is often smaller than the original data set, and you will just fine tune it a little bit. So update the weight slightly so that it gets better at your specific task that you wanted to do. Or with the new GPT model, they even say that like fine tuning is not really necessary anymore, like it's a bit in between. But that you can just, because a generative model, what you can do is like you give it text and then you let it model language and let it generate a logical consequence. And this way you can also have different tasks implemented. For example, you can prompt it for knowledge. What you can do is like give it a text and see if it can know, if it does know that New Delhi is the capital. And or you can give it some examples to show you what do we expect. And then hopefully it gets better at it. But then you don't do anything of pre-prompting, you just use a fully trained such a large language model and use it for inference. So yeah, this is quite basically what are these language models and what do they mean, and what do they mean in the field of NLP. What I will now try to go in detail is more in detail about is like transformer, so the architecture behind and why certain choices were made in this architecture. And what I can tell you is like the most important part in this transformer model is actually the attention part. So that I will try to explain a bit deeper. But first, to give like a very high level overview of the original transformer, I got some inspiration for the images from a very good blog that I linked here. So if you want to, if you want to get more information, you should go to this link after this talk. So what you see is this is the original transformer that was once made, and it contains two big parts. You've got the encoder and the decoder part. So what you do, for example, your inputs, in this case, we see an example of translation. So what you would do is you input the text into these encoders. They would generate a new type of embedding for this text. You pass it to the decoder, which will then generate hopefully a useful translation. So if we then go a little bit deeper into this architecture, we see that these blocks that we saw here, I don't know if you can see my pointer, but the blocks that you saw here actually contain of 6 layers of smaller blocks, which also called transformer encoder and transformer decoder blocks. And then when we zoom in one of those blocks, we see that it contains different components. So it contains 2 important ones. It contains a layer of multi-head attention, which I will explain later on in more detail. And then it has a feed forward to add nonlinearities into the network. But then we have the residual and the layer norm, which are actually also important, but they are more for the convergence. So to make the training a little bit better. So I won't really go into detail for those. So let's maybe start with the first layer and let's start with attention. To explain why attention could be useful, I have another example. So this is an example of machine translation. Before we knew about transformers, what we did there in natural language processing was using recurrent neural networks, which means you handle text sequentially. So in the first step, you would feed in an embedding of the first word that you wanted to translate. This network would then generate a hidden state that would pass on to the next step, where you feed in this hidden state and the next word, and so on, until in the end, you get actually a hidden representation of this entire input sentence. So then you have got a representation of I am a student. But then you want to start decoding this I'm a student because you want to start translating. So you will input this hidden state of this, which represents this entire sentence, together with the first start and sentence token. So then you know I need to start decoding, and you start your decoding. But you can clearly see a weak point in this architecture, because to translate je, you of course you need most information about this word, the I word. But as it has passed through all the steps of recurrently, actually the I word is less represented in the final representation of the sentence. So what we did in machine translation was add attention to go different direction to solve this. So what you had is like you have this hidden state query. So you have the hidden state at this moment, and we want to define which of these hidden states that we saw earlier are most useful for this translation. So we will do again, and this time we do dot attention. So we take the dot product between the query and this hidden state, the query and this hidden state, which we call the key then. And we will get a value. For example, we see that I gets 0.5, but we can do this for every case, such that we know in this time step, actually, this hidden state is the most useful. So to translate je, I is the most useful translation. So in the next step, we then try to, again, make this entity-weighted embedding, where we have a higher highlighting on the I than on the rest of the sentence. And then we input this to find the right translation. So what I have shown with this example is that attention can be used to have long-range dependencies in text. So if you want to refer from a certain time back into time, or maybe into future, attention can be very useful for this. So what I now explained is why multi-head attention allows long-range dependencies, but now I will go in more to detail how attention exactly is applied in transform, which can become a little bit confusing. So I will start to explain this layer. So we are at the moment that we have this word embeddings, and we will feed them into the multi-head attention. So for example, we've got mathematical representation of these two words, and we will feed them in the first layer of our transformer, the self-attention layer. How does attention work in transformers? So therefore, given that we have this embedding, so we have these embeddings and we feed them into this self-attention layer, the first thing that they will do is they will multiply these embeddings with weight matrices. And this weight matrices will generate 3 separate values. So you will multiply this embedding with 3 different matrices, and this will give us 3 different values, as the same as here. So then we have again this query key and value that we saw in machine translation as well. This allows us then to, for example, starting from here, query, use this query and compare it to all the keys you have of the sentence. Because when you have transformers, we feed in all the inputs at once. So what you do is you will take this query and compare it with the other words query, etc., and get this attention score that says like, for this word, actually the word itself appears to be most important, and intelligence gets this important score. We again apply a softmax to make it like probabilities, and then we apply this importance score or attention score with the value we have and sum this. And this is exactly what the self-attention layer does. So it takes this input embeddings and creates new embeddings for that word, depending on the other words that you feed into this network using attention. So what you can see is that attention is omnidirectional. So it allows from one word to look to any other word in the sentence that you have put into this transformer network. So that's an important one. And then to make it even more complicated, we added an extra layer of attention. So instead of, you can have different weight matrices that you can multiply with this base input, so that you can have different types of queries and apply different types of attentions. So that's what multi-head attention does. So now, but there is one thing about this omnidirectionality. Of course, in your input sequences, it doesn't matter. You can really look to all possible embeddings at the time that you feed it in, because it's given. But when you want to decode and generate text, you do this word by word. And to generate one word, you can of course not look in the future, but you have to look to the past, the words you saw in the past. So that's the main difference between transformers and encoders and transformer decoder, is that in a transformer encoder, you just have this full self-attention system, while in decoder, you won't allow the self-attention to go to words or embeddings in the future. So you have this masked attention. So this is that. And then one other important part, so now we have to understand what self-attention is. We feed all these words in together, but what you see is that it's omnidirectional. So this self-attention doesn't show any sequence anymore in text. So it just combines words depending on these keys and values, but it doesn't really take into account which words are next to each other. And actually the sequence in text is quite important. So what you do is instead only you transforming this D into a word embedding, you will also add a position embedding, which reflects in which place each word is. So now we have almost every very important part of the transformer. So we had all word embeddings, our sentence that we feed into this network. Then we have these word embeddings and position representations that we will feed into this multi-head attention, which will allow us to have this omnidirectional and long-range dependencies. And we then fill it into feed-forward neural network. And then we repeat this for every layer. And this is how the transformer models nowadays grow, is they just add more layers or more attention heads, etc. And of course, more data. So now you know a little bit about what transformers are, so the basic on transformers. And what I now will try to explain is that we've got three big different types of transformer models. So we've got transformer models like the ones I just explained, which do like sequence to sequence. So they take a sequence and they will generate a sequence. And they're the very famous one is T5. Then you've got encoder models, which only use the first part. So there is no masking during the pass through. So there you just take an input sentence and pass it fully through. And then we get to the BERT models, Roberta models, and all this type of models. And then we've got the other ones where you take the second part. So you take the decoder part, where we will generate text. So this is like GPT-3, GPT-J. I think by now, recently, GPT-Neo X was generated, which is like a very open source GPT model with 20 billion parameters. which is fully freely available online if you have the resources to use it. So then, to give a concrete example, what is a sequence-to-sequence model is, what you can do with this is you can, for example, ask him to do machine translation by saying, please translate English to German, that is good. And then it passes through this entire scheme and will generate that is good. Then we've got BERT models. What do we know about BERT models? That they don't use masking, so that we can't really do this language modeling in the more traditional way that says like, given this word, predict the next one, because it looks at the words in the future as well. So what we do is we input one sentence and we want to mask one, or we actually input two sentences and then we mask one word in the sentence. And we ask to predict this masked word to transformer. And this allows us to handle this text bidirectional. So this is a very strong advantage of encoder models. And this is not all. We also want encoder models to learn the sequence of text. So how on sentence level, so how sentences follow along. So what we do is we actually enter two sentences separated by a separation token. So for example, my dog is cute, separated by he likes playing. And then you ask the transformer model, please predict whether my dog is cute and he likes playing are two logical following sentences, or if there are two random sentences that are put together. And then we've got, of course, the decoder models, which is shown by this animation, where you input a part of the model, and then step by step, you will generate the next one, which is like the more traditional way of language modeling. And this way was how GPT-2, GPT-3, and so are formed, which you can try out online. As we are in the Swedish environment, maybe it could be useful for your organizations to know a little bit what the state of the art is currently in the Swedish NLP. So I will go over this in three parts. First, I will say which data sets are available, because that's quite important. If you want to train a language model, we of course need our data. Then I will say which models are currently available that are already trained and can be used from Hugging Face. And I have, for example, a very short use case, but probably you have more interesting use cases than I do. So what do we have? We've got the first part. For the pre-training, we just need Swedish text corpora. And so therefore we can use Swedish Wikipedia. We have some Swedish books at Litteraturbanken. Then you have the scrolled corpus, Oscar. But as you see, these are all in the range of gigabytes. And actually the real big models in English are trained on terabytes. So we're still actively working on gathering more Swedish text data. So if you have Swedish text data available, let us know. And then we share it with public, because it could be very interesting to train these large Swedish models to have the same performance for the Swedish text as we do for the English text. Then we have the second stage, because we had this language model, and the second stage, you want to fine tune it on certain specific areas. Therefore, we also need Swedish data sets for that to do, for example, Swedish name entity recognition. And such a corpus is available. We also have some sentiment classification and a machine translation data set that is a work in progress. And then the last part of data that we need, so of course you see we need a lot of data to handle these models, is an evaluation, because we have these large language models now, but how do we evaluate? How do we know really which one is better and which one is worse? Because one task doesn't really show this. It's maybe a model that's better at one task, but the other model could be better at another one. So this is still an open challenge and work in progress as well. So we have this project at AI Sweden called SuperLim, which tries to create this data set where we've got 13 different tasks to evaluate language models on. But currently we only have test data available, but hopefully the train and the validation data will come soon. This is still work in progress. And then currently which models are available. So we've got our first decoder model, but this is not yet open source. This was trained by a collaboration between AI Sweden and RISE. It's called GPT-3, but it's not open source. just because we don't know yet what this decoder models can do. For example, we got all these stories about, for example, models recommending people to put their fingers in sockets, which is not the way to go. So that's still, before we give it to the public, it needs to be explored further. Then we have a sequence-to-sequence model. The ones, like I explained, the original transformer, we don't have any Swedish model like this yet. And then we've got a bunch of BERT models, so encoder type models, where from a lot are available on Hugging Face. And then to give a short use case is wherefore could we use these models? If you work in for example, a sketchbucket and you want to anonymize some data, what you could do is take this text, use named entity recognition, which can be performed by these models. And for example, in this case, we want to remove Severine such that this word, this sentence that we use and want to spread is not longer harming privacy issues. So it can be used for anonymization. And now I give like a little, so now I've explained what transformers are, that they are these very big models, that we have a starting point of transformers in the Swedish field, but currently there are some active challenges for these language models. Ones I have briefly mentioned before, but I think it's useful to mention them again. The first one, which is very active at the moment, is what do we do by the ethical consideration? Because we are humans, we generate data, but human beings are inherently a little bit biased. So our data is also biased, and these models really reflect this bias. What can we do? How can we solve this? Because for some parts, you don't want this bias. And then we have this evaluation in NLP, which is a big challenge because we now have these big language models, which can do amazing things, like that you can have conversations with them. They feel very realistic. But where does it like end? And how do we handle the evaluation? What can they really do? What can't they really do? Where can we use them? Where can we not use them? And how general are these models? Is also a big question. So, and these are some acknowledgements of the where I got some materials from. As I said before, if you're interested in transformers, please go and read these blogs. These are really good. And if you've got a very deep interest in NLP, this is a very interesting course, I would say. So I think this was my part on transformers.
Yeah.
I hope you survived it.
Super interesting.
Can I ask, will there be a time for questions?
Absolutely. We take questions first, and then we can go to the breakout rooms. Absolutely. Please go ahead.
Sorry, I have to